Mars' polar ice caps were among the first Earth-like features identified on the red planet. Since the development of film in the 19th century, researchers have been expecting to observe Earth-like activities such as ice flow at the Martian poles. However, Mars has consistently defied these expectations. In 1971, data from the Mariner 9 spacecraft provided the first images of the southern polar ice cap on Mars, sparking a 50-year debate about whether the ice was flowing. Every time a suggestion of flow emerged, it was swiftly contradicted by new observations. For 5 decades, scientists have struggled to explain the stagnant nature of this Martian ice. Now, a new paper led by senior scientist Isaac Smith of the Planetary Science Institute offers a potential answer. The ice, consisting of various material layers, might be held in place by these very layers. High-resolution images of Mars' polar ice caps reveal complex, layered structures. These caps are approximately 2 to 3 kilometers (1.2 to 1.9 miles) thick and extend over more than 1,000 kilometers (600 miles) across the Martian poles. Composed primarily of water ice, these caps overlay a complex landscape of steep slopes and cliffs. Researchers had anticipated that ice flows in these regions could reach speeds of up to 1 meter per year, with even the most conservative estimates suggesting a flow of 10 centimeters per year. Such movement would be observable in images taken by modern missions, which can resolve features as small as 1.2 to 2.4 meters for 2 to 8 feet. Long-term flow would also be evidenced by moraines, depressions in icy cliffs, and bending of layers. None of these features have been observed in the polar caps. Given the absence of observations supporting ice flow, Smith poses the question, why is the ice moving slower than expected, and how slow is it? In his paper titled An Observable Flow Hypothesis in Mars Polar Layered Deposits, published in the journal Icarus, Smith explores for different scenarios through complex calculations. Ice is too cold to move. Atmospheric contaminants slow the ice. A homogeneous material mix slows the flow. Layered ice creates unique conditions that significantly slow the flow. While all 4 hypotheses seem plausible, mathematical models indicate that in the first 3 scenarios, the ice should still exhibit observable movement and leave evidence behind. Only the final scenario, involving layered landscapes, showed ice remaining fixed in place. Layers are like making s'mores or Oreo cookies. You have hard layers with soft layers in between. If you stack enough Oreos and press down, there will be some flow, but not as much as if the Oreo mix breaks apart, Smith explains. The layering model can slow things down by several orders of magnitude, matching the observed lack of movement. Layers are like making s'mores or Oreo cookies. You have hard layers with soft layers in between. If you stack enough Oreos and press down, there will be some flow, but not as much as if the Oreo mix breaks apart, Smith explains. The layering model can slow things down by several orders of magnitude, matching the observed lack of movement. Referring to the work of Percival Lowell in the late 1800s and early 1900s, Smith notes, researchers have been thinking about Mars polar caps since Lowell. Lowell even imagined flowing ice and canals to help inhabitants on Mars. To make accurate statements about what is happening on other planets, we need to understand basic physical principles. This is quite an esoteric topic. Very few people are interested in ice sheet dynamics on other planets, but many more people care about the history of ice on Mars. Without the right context, we could be misled for decades. Getting it right means knowing which processes are active and which are not. I think this paper brings us closer to understanding why the ice on Mars behaves in such an inert manner.